Right? The important things like the sine wave, calculating the frequency in the period, and you should know that the frequency is calculated in terms of hertz, and the period is calculated in terms of the time of the seconds. Right? So we have done some examples there. Remember the periodic signals. Right? Periodic means they make the same pattern throughout. The other one is the aperiodic or the non-periodic, you say. So three things we have looked at: the frequency, the period, and the phase. Yeah, I guess we are supposed to start from here. The wavelength and the period. Okay. So it says the wavelength is the distance a simple signal can travel in one period. So the distance measured in probably meters or millimeters or kilometers, right? The distance. So it says wavelength depends on both the frequency and the medium. Medium basically means the type of communication channel that is being used. Eh? And given the diagram there, the transmission medium at time t and transmission medium at a particular time. So that is the wavelength, one complete cycle, the time that it takes for it to travel from one point to the other. Wavelength can be calculated if one is given the propagation speed, okay? And the propagation speed is the speed of light and the period of the signal. So it says if we represent wavelength by the lambda symbol, right? Is it, students? What symbol is it? Lambda symbol. Yeah? So it says if we represent wavelength by lambda symbol, it says propagation speed by c, which is speed of light, and frequency by f, we get. Okay. So in order to calculate the wavelength, the formula is given there: propagation speed times period, which is equal to propagation speed over frequency. Yeah? So the wavelength is normally measured in micrometers or microns instead of meters. So for example, the wavelength of red light, it says frequency is equal to 4 times 10 to the power 14. So it says in AI it is lambda is equal to c over f. Right? Now 10 to the power 14 is the speed of is it the speed of light? What is the speed of light? Okay. 3 times 10 to the power 8. Eh? Okay. It. Still clarifying it here. The wavelength of red light. To all right, so here it is given. The light is propagated with the speed of 3 times 10 to the power 8 meters per second, right? So that C is given in this case here. So the wavelength is normally measured in micrometers instead of meters. So for example, the frequency is already given, that is 4 times 10 to the power 14. Therefore, the wavelength, which is same as propagation speed, and propagation speed is the speed of light. It says here. So using that speed of light, that is 3 times 10 to the power 8, and the frequency for this example here, which is 4 times 10 to the power 14. So once you calculate that, you get your answer as 0.7 micrometers. That means one complete cycle covers that length. Okay, that is 0.75 micrometers. So this is the example that it is referring to here. So it says in coaxial or fiber optic cable, however, the wavelength is shorter, and that is 0.5 micrometers because the propagation speed in the cable is decreased. Now, why it is saying this is, I guess, the speed of light. Okay, that is just one parameter that is assumed to be used, because if you are using fiber, fiber optic, then the signal is in the form of light. So that is why it is using the speed of light in this case. So in case you do get any questions on calculating wavelength, then this is the formula, right? Propagation speed over frequency, and the propagation speed is basically the speed of light. Okay, that's the default value that is being used here. Okay, then the next thing talking about is the time domain and frequency domain plots of a sine wave. Now, that means representing the top diagram. Okay, this is a time domain plot, because time domain, how is a time domain? Because it's running the time, right? We have the time in the x-axis, and the other way to represent the same diagram is to use the frequency domain. So here in the x-axis we have the frequency. So if you look at this diagram on the top here, what is the frequency? Frequency is 6, okay, and the amplitude is 5. So there is just one straight line or a vertical line. Okay, same thing represented using the frequency domain. So sometimes you may have several the time domain plot, the several sine waves, right? And the same represented using the frequency domain plot. Okay? So here in this case, if you look at this example itself, it says the time domain representative of 3 sine waves with frequencies 0, 8, and 16. Okay? 0 frequency, what does that mean? No cycles at all, or the cycle is just on the x-axis, right? So in this example here, 0 frequency, because here you see only 2 sine waves, right? 2 sets, one with the frequency of 8 and the other one with the frequency of 16. The 0, 1 is not showing here, and in this case the 0, 1 is that straight one you see on the top. Okay. The 15, the horizontal line. So that is right here. Okay. If you see a sine wave with 0 frequency, that means on a frequency domain plot, right here, and then the one with the frequency of 8 with the amplitude of 10, and the other one with the frequency of 60 with the amplitude of. Says a complete sine wave in the time domain can be represented by one single spike in the frequency domain, right? So one single spike in the frequency domain. The frequency domain is more compact and useful when we are dealing with more than one sine wave. So like we are dealing with the more than one sine wave. So this is much a better way to represent that rather than that one. So that will get messy if you have more sine waves. Better ways to use the frequency domain plot. Says a single frequency sine wave is not useful in data communication, and we need to send a composite signal, that is a signal made of many simple sine waves. So in reality, there is no single sine wave that travels through the communication. There are many sine waves, right? Multiple. So in order to represent that multiple sine waves, it's best to use the frequency domain. Some examples of this, okay, or maybe one or two questions just to showing you how the frequency domain and the can be changed or converted or drawn. Okay, this is one example here of a frequency domain graph. Right? Another one is here. Not much questions on this one, but a common question that usually comes on this type of question here or this type of graph is to calculate the bandwidth. Okay? So in order to calculate the bandwidth, the formula is the bandwidth. It's a very simple formula. Okay, it is the bandwidth is equal to the highest frequency minus the lowest frequency. Okay? So if, for example, we look at one of these here, the highest frequency in this case is 16, and the lowest frequency is 3. So the bandwidth in this case is 13. That is the bandwidth in this case. This example here. Another one here. What will be the bandwidth in this case? So there is a difference of Kn. So in this case, this will be 190, 180, 170, 160, and 150. So 150 will be the lowest. So 200 minus 150, and your bandwidth will be 50 Hz. Right? Yeah, these are maybe one or two questions there. Sometimes you may also get a question to convert the time domain plot into the frequency domain plot. So that is like this can be given and you are asked to draw this, right? So by looking at the frequency, you should be able to draw the frequency domain plot, okay? Right, moving further, talking about composite signals. Composite signal is when you have more than one signal, right? So it says can be periodic or non-periodic. A periodic composite signal can be decomposed into a series of simple sine waves with discrete frequencies that have integer values. So if you have a periodic signal, composite signal like this one here, then it is very easy and simple to put it on the frequency domain with discrete integer values, right? Because you know exactly how many complete cycles are. But if you have a non-periodic signal, then it is difficult because you cannot measure, right? Because non-periodic, that means some signals are normal, some going up, some smaller, some bigger. Okay? So that way it is difficult to measure, right? So it says a non-periodic composite signal can be decomposed into a combination of an infinite number of simple sine waves with continuous frequencies and frequencies that have real values. Real means real numbers, right? Means decimal values. So it says if the composite signal is periodic, the decomposition gives a series of signals with discrete frequencies, means normal numbers, discrete, okay? And the other one with continuous. And here says this figure shows a periodic composite signal with frequency f, and this type of signal is not typical of those found in data communications. So it says we can consider it to be 3 alarm systems, each with a different frequency. The analysis of this signal can give us a good understanding of how to decompose signals. So this is a periodic signal here, right? And according to that, it says 3 sets of signal, okay, with maybe 3 different alarm systems sending some sort of signal. And the same signal here, okay, if they are periodic, you can always put it like that. Okay. So there are 3 sets here. So one with the frequency of f, the other one with the frequency of 3 times the first one, and the other one which is the 9 times the first one. And also the representation of the same, okay, given in the frequency domain, that is given below that. F3, F, and 9. So we're just using F as the algebraic representation there. Okay. Right. Whether the figure 3.11 shows a non-periodic composite signal. It can be the signal created by a microphone or a telephone set when a word or two is pronounced. And in this case, the composite signal cannot be periodic because that implies that we are repeating the same word or words with exactly the same tone. So this is an example of a non-periodic signal here. Right? Now to represent that, okay. Now so far, if you have to differentiate. We have looked at the periodic signals and we have got the frequency domain plot for the periodic signal. Means we can get the exact values. Okay. Now with this one, there is no exact values. There is no discrete values. We don't know if there are 3 frequency or 10 frequency or whatever, right? So in this case, it is said to be real, right? It's not discrete but real. So to represent the non-periodic signals, okay, on the frequency domain plot, we have to put it something like this. That from there, here and all, because it is including all these little values. Because that is here, right? Okay, and the maximum amplitude also shown there. Okay, then here comes the bandwidth question here. So we just look at that. The bandwidth of a periodic signal is the highest bandwidth minus the lowest bandwidth. So that's for the top one, right? That is 500 minus 1000. So that means there are so many discrete sine waves, discrete signals, right? Starting with 1000 being the smallest number of signals, small frequency, and the 5000 being the largest frequency. So to calculate the bandwidth, it's going to be 4000. Right? The second one, right? It is showing the bandwidth of a non-periodic signal. So the smallest frequency in that case is 1000, and the highest frequency in this case is 5000. And the inner frequencies here, the in between the highest and the lowest, it's not known. It's the real numbers. So that's why it's all shaded here. Another example here. It says if a periodic signal is decomposed into 5 sine waves, right? 5 sets of sine waves, with the first one having 100 as the frequency, 300, 500, 700, 900. What is its bandwidth? So it's very simple here, and it says draw the spectrum, assuming all components have a maximum amplitude of 10 volts. And in this case, if we have to draw, that is how we can draw it. Right? This is periodic signal, so it's exact values, right? 100, 300, 500, 700, 900, and with a amplitude of 10 volts, and the bandwidth given there. Okay. Another one says periodic signal has a bandwidth of 20 hertz. So this example here, that means it is already giving us the bandwidth. Okay. So we said 20 hertz is equal to highest frequency minus the lowest frequency, and the highest frequency is 60. What is the lowest frequency? So basically, we're looking for that X value. So for X will be what? X will be 40. So we'll say the lowest frequency is 40 hertz. Right, and says the spectrum contains all integer frequencies. Show them using the spikes. So that is how you can show the frequency. Yeah? Non-periodic signal, okay, has a bandwidth of 200. So bandwidth of 200 kilohertz, right, in this case. And if it is given in kilohertz, then we will assume that the highest frequency and the lowest frequency will also be in kilohertz. Right? So bandwidth is 200 kilohertz with a middle frequency of 140 kilohertz and peak amplitude of 20 volts. The two discrete frequencies have an amplitude of 0. Now the two discrete frequencies meaning the starting and the ending frequency. Okay? And it says draw the frequency domain. So it is going to be something like this. Highest middle, we know the middle one, right? 140. And we don't know the lowest one. And we also don't know the highest. Right? So we can say x1 and x2. Right? The lowest, the highest, middle one, and the peak frequency is the peak amplitude is 20. So in this case, a diagram something like this. Right? The state. Because it is a non-periodic signal. And let's see. Okay, there you go. So the question also is to calculate. Okay, anyway, the question doesn't ask you to calculate, but how can we calculate the lowest and the highest frequency? How do we get 40 and 240? The one thing we know is the 200 kilohertz. Okay? That means x2 minus x1 is equal to 200, right? So that means there are two unknowns, right? Two unknowns, x2 and x1, which is equal to, so that's one formula you get, the one equation you get. How can we derive another equation? Using 140, which is given. These types of questions do come in exams. 140 is the midpoint. Come on, mathematicians. How do we calculate the midpoint? Between two coordinates. What is the formula? We'll say 140 is equal to x 5. What is the midpoint formula? Okay. Plus or minus? Plus, eh? So you got another equation with the two unknowns. So we can use what? Simultaneous equations here, solving simultaneous equations. Substitution or elimination, which method? Okay, so let's do this. So we will say x2 equal to 200 plus x1. Okay. Plus x1 cancel, plus x1 here. So I'm going to substitute this here. Okay, so that means this has to go there. And if you do that, 140 is equal to x1 plus 200 plus x1 divided by 2. That is multiply by 2, you get 280. 2x1 plus 200, you get 2x1 is equal to 80 and x1 is equal to 40. Yeah? So that's your 40. That's what the diagram shows you there. And once you know the x1, right? So you can calculate x2. So we can just substitute in the best formula. 200 is equal to x2 minus 40 plus 40 plus 40. X2 is equal to 200. So these types of questions do come. We can maybe see one or two there. Maybe some questions in the tutorial. Okay, there's one here. Let's try and do this one. Done. So in this case, the two extreme, that is the starting and the ending point, has an amplitude of 0. So the bandwidth is 300 kilohertz and middle frequency is 180. You have to draw. So when you are drawing it, make sure before you draw it, you have to find out the other frequencies. Yes, what are the extreme frequencies? 30 and 330, all of you getting that? Right? And so your diagram will be similar to this one here, 30 and 330, and then straight up and forming a triangle. Okay, let's look at this one. This question was, or rather is from 2020 paper, final exam. This one. So make sure you label all the necessary points on the axis and label the axis properly. Now, in this case, the extreme frequencies have an altitude or amplitude of 10 volts. So here, your diagram will be a bit different. 10 volts. So that means your diagram will go here, like that, and then like that. And this is your network. Your X1, X2, and the state. And the maximum amplitude also 20 volts. Note that one. Okay, looking at the next slide. So another example here says an example of a non-periodic composite signal is the signal propagated by an AM radio station. In the United States, each AM radio station is assigned a 10 kilohertz bandwidth, and the total bandwidth dedicated to AM radio ranges from 530 to 1700 kilohertz. That's just an example. Another example of non-periodic is the signal propagated by FM radio station, and they have a different bandwidth. Digital signals. So it says so far we have looked at the analog signals, and in particular we have just looked at the sine wave. Right? So there are a couple of things that you should know about that. Right? That is how the sine wave is represented. You should be able to calculate the period in the frequency in the sine wave, and also you should be able to represent the sine wave using a time domain plot as well as a frequency domain plot, right? And then we have also looked at the non-periodic signals and how the non-periodic signals can be represented. Okay, non-periodic signals, for example, okay, this one here, right? And then representing that in the frequency domain plot. Okay, so these are some like simple or some types of questions that can come. Like you can also, we have seen that in the past year exam papers as well. Okay, so that was more of analog signals. Now the next or the subtopic here is about digital signals. So it says in addition to being represented by an analog signal, information can also be represented by a digital signal. So for example, a 1 can be encoded as a positive voltage and 0 as a 0 voltage. Digital signal can have more than 2 levels, and in this case we can send more than 1 bit for each level. So given this diagram here, now this is 2 digital signals, one with the 2 signal levels, in the other with 4 signal levels. So look at this example here. 2 levels, level 1 and level 2. 8 bits sent in 1 second, and the bit rate is 8 bits per second. So in 2 seconds, what will be the, or how many bits can you send? In 2 seconds, you will send 16 bits. And likewise, in 3 and 4. The second diagram showing a digital signal with 4 levels. So in using 4 levels, you can see that you can send 16 bits in 1 second. And the bit rate in this case is 16 bits per second. Okay, BPS, bits per second. Example, a digital signal has 8 levels. How many bits are needed per level? We can calculate the number of bits from the formula. Okay. So there is a formula given there, and to calculate the number of bits. Now just looking at the previous diagram here, okay, you can see that if you are using 2 levels, the number of bits at each level is just 1 bit. Eh? With 4 levels, there are 2 bits at each level, right? Or at each time, you can say. So if you are using 8 levels, how many bits are needed per level? So in order to calculate that, and the answer is already given there, says log 2, okay, or with the base 2, and then the 8 levels, you'll have 3 bits per level, right? And how do we get that? Yeah, basically, is logarithmic. We can just change that to base index form, I guess. For example, we say x is equal to log x. So changing that to base index form, you can say 2 to the power x is equal to 8, and in this case, x is equal to 3, and 2 to the power 3 is equal to 8. Now there is another way to solve this, right? What is the other way? Like here we can say this like more of a trial and error method. Eh? You put 1 and then you put 2 and you put 3 and then you go inside. Right? It's a trial and error. What is the other way of solving? I think you will be like this. Log log. Your calculator has what base? Log. Log base 10 or base 2? I think it's just log log. Right? Your manual calculators? So we say 8 log divided by 2 log equals 3. Your manual calculators, does it give you the same? Yes. So if you have like any number of values, okay, the next question for you. Digital signal has 9 levels. How many bits are needed? Okay, do it. Let's see. So 9 levels. So it says 3.17, but that is not realistic. It says there. So each signal level have represented 3.17 bits. However, since the answer is not realistic, the number of bits sent per level needs to be an integer, as well as a power of 2. So in this case, 4 bits can represent one level. Right? Okay, moving further here says another term that is bit rate instead of frequency is used to describe digital signals. So the bit rate is the number of bits sent in 1 second expressed in bits per second. So sometimes they call it frequency and sometimes they call it bit rate. The frequency is when you are using analog signals, and bit rate is when you are using digital data, digital signals. One example here, I think this question is based on bit rate. So it says, assume we need to download text documents at the rate of 100 pages per minute. What is the required bit rate of the channel? So assuming that a page has got 24 lines on average and 80 characters in each line, and one character requires 8 bits. So the bit rate in this case is 100 because 100 pages by 24 lines by 80, right? And then by 8. And that gives you 1536 and divide by 60 because 60 is what? 60 seconds in a minute, right? So that gives you an answer of 25,600 bits per second or 25.6 kilobits per second. Okay, before we go further, one or two examples on this one. Okay, here, this one. This question, this should be microseconds. The last one, 29. So bit rate, basically the formula. What is the bit rate? take it. It is equal to what? That is the time taken to send the number of bits sent in 1 second. Right? So, bits sent in 1 second. That's what the bit rate is. So, for example, if you look at the first one, for another, you can say, in other words, I think it's a bit length divided by something. Okay, just give me a second. Let me find out. If it is the number of bits sent in 1 second. So right, so if you look at the first question here, it says a signal in which one bit lasts 0.001 second. So number of bits sent in 1 second. So then we have to, it's like a ratio based thing. Yeah? So we know that we are looking for X, which is the bit rate. And we also know that one bit gets passed in 0.001 second. We are looking for something that we can pass in 1 second. We are technically looking for the X. So how can we solve this? Cross multiply. So we can say 0.001 X is equal to 1. So divide by 0.001. So left with X is equal to 1 divided by X is what? So the bit rate is 1000 bits per second. We do the second one and the third one. Second one is, remember, milliseconds. So you have to convert this to seconds first. And then the third one is microseconds. Okay. That some Then second one, what's the answer? What is the bit rate? 500 bps. Okay. And the third one? Yes, answer for this. Signal which 10 bits last 20 microseconds. What is the bandwidth or the bit rate? Hmm? 20 microseconds converted to seconds. First, how much? $500 kilobits per second, or you can say it is just bits per second, then what? 500,000. And you can see that formula given here. This bit rate is equal to 1 over bit duration. Another words we can say like 1 bit duration. Simply here you can see how it is calculated. The solution. Every value is converted here will be converted into seconds. Very simple. Either you can use the this method or use that way. It should give you the same answer, right? Okay. Now the next set of questions there is a similar type of question. Says a device is sending out data at the rate of 1000 bps. That means the bit rate is already given to you, and here is asking you for the time it is going to take. So you said, for example, 10 bits or 8 bits or 1000 bits. So for the first one, for example, if we are using this formula here, then you know the bit rate is 1000. The bit duration is something which we are looking for. How long is the time? So what will be the answer? Is it correct? So x is equal to one over 1000 and x is equal to 10 over 1000, which is equal to 1 over 100, which is equal to 0.01. So that means it will take 0.01 seconds to send 10 bits at the rate if the channel has the rate of sending data at 1000 bits per second. Okay, do the other two. Yeah. Okay, so the second one, 8 bits. A single character is 8 bits. So if you do it same way, the answer should be what? 8 divided by 1000, right? Zero point 008 seconds, right? And the third one is 1000 characters. So 1000 characters you have to convert into bits. Eh? So one character is worth 8 bits. So 1000 characters will, sorry, 100,000 characters will be 800,000 bits. So in that case, you'll have to do this 800,000 bits divided by 1000. So it will take 800 seconds. So just keep this in mind. These types of questions can come. Bit rate, and this one was we say bit duration. How long it takes for certain data to be sent. Okay, another question there that I want you to look at is question number 17 in your tutorial here. This is again, it's a question of how long, right? So we are looking for time, remember? Whenever I say how long, then we're looking for time. So the file contains 2 million bytes. 2 million bytes. And it says, how long does it take to download this using a 56 kilobits per second channel? Right? So 56 kilobits, we can leave it at kilobits per second, or we can convert it to bits per second. So let's say we want to just leave it to kilobits per second, then how will we do this one? Bit rate is given. The 6 years. Converting that 2 million and getting the regular text. So 2 million bytes, you convert into kilobytes, assuming that we are just multiplying by 1000 rather than multiplying by 1024. I hope you remember this. 1 kilobyte equal to the power 10. What is 2 to the power 10? for simplicity purpose, right, we usually just use the 1000 rather than using 1024 for simple simplicity. We just use 1000. Eh? So 2 million bytes, 2 million. We can either convert this into bits or we can convert it to kilobytes. If we just convert this to kilobytes, bytes to kilobytes, we have to divide by 1000, 2000 maybe kilobytes. What's next? Which way is easier? We convert that kilobits and make it just BTS. Instead of this, say 56,000 BTS rather than kilobits multiplied by 1000. Think. Any idea what to do there? Okay, so what we can do is first we will we have already converted this one, right? That is 56 kilobits per second, so it's like 56,000 bits per second. Kilo means thousand, right? That's how we will take. So we will also convert that 2 million bytes into bits. The 2 million bytes into bits will be what? Times 8. Remember, it's going to be 8. 8 times 16, right? 16 million. So let's put 16 million there. And we should be able to calculate the value of x. Because this is BPS and this is also in bits. So both of them have the same measurement there. So if you are using the 56 kbps channel, then it should be 16 million divided by 50. We can just put it upside down. X. So 16 million goes here. And your answer in this case should be what? 2. Or we can just round it off to 286 seconds. Right. So that was using 56 kbps channel. If you are using 1 megabits bits per second channel, that means instead of this, you will use 1 million. 1 mega, so that means 1 million. So 1 million. Yeah. So in this case, your answer will be what? If million divided by 1 million, that's going to be what? 16 seconds. Right, I want you to do this one here. This question from one of the past year exam papers. One gigabytes of data using 1024 kbps channel. So again, for simplicity purpose, 1 gigabyte will be what? You have to convert into bits, right? So 1 gigabyte is equivalent to how many? How many bytes? 1 billion bytes, right? So 1 billion times 8, eh? So that will be 8 billion. So what should be the answer? Done? What's the answer? That should be 1 billion is what? 9 zeros? Divide by 1024,000, eh? 976.5 seconds or 0.6 seconds. Is it? Yes. Okay, that's one calculation you can do. Now, in case if you want to really get the exact value there, as I said, we are just multiplying by 1,000 and a million and a billion. But if you want to do the exact gigabit, so it will be 1 times 10 to the power 9. Okay. 2 to the power 2 to the power 9. What is 2 to the power 9? 2 x y 9. No. Something wrong here. Not 2 to the 10 to the power. Two to the power 10 is 1024 to the power 20 for the billion million 2 to the power 30. 2 to the power 30. This will be the exact number of bytes. Okay. I just said like we use 1 billion for simplicity. So for your exam papers, we can just keep it to the 1 billion. So if it is 1 megabits per second, then you just multiply by 1,000 bps. Okay. Or if it is 1 gigabytes, you will just say times 1 million. But the exact value to use will be 2 to the power 30. So this divide by, and also that 1024 we can multiply it by 2 to the power 10. 1024 multiply by 2 to the power 10. So your answer will be 10487,576. For the first one, we have to convert into bits. 1 times 2 to the power 30 times 8. That will convert into bits. Then divide by 1024 times 2 to the power 10. That will be your exact answer, the correct answer. If we are using the exact values, okay, 2 to the power 10, 20, and 30. But if we are just using a million, a billion, then answer will be a bit different. Okay. Okay, the rest of them is mostly theory here. Talking about baseband transmission and broadband transmission. A baseband basically says that sending a digital signal over a channel without changing the digital signal to an analog signal. That means you can simply send the whatever signal has been generated by the computer, okay, to another computer without converting it into digital analog. So these network cables that you see connected to the computers here, these are digital cables. That means you do not have to convert it to analog. If you want to send it outside FNU from here to maybe another campus, then of course it goes through your data goes through the telephone line, and telephone line only takes in the analog signal. Right? So that has to be converted. So that type of signal is known as the broadband signal. Okay. Baseband, and the other one is broadband. Broadband is where your digital signal has to be converted to the analog signal for transmission. And these diagrams, they are not so important here because they are high level diagrams, but here just talking about the conversion. So it's usually the job of the modem to do the conversion, digital to analog and analog to digital, right? So not so much of theory, but remember the calculation is important. As you can see, it comes in the exam papers there. Okay. Apart from that, the tutorial question that you see there, there are few other things we are supposed to look at, like attenuation, the bit length, okay, with the propagation speed, and also talking about delays. Now the other part here is covered in our next lecture, okay? That is lecture 3, which is talking about transmission impairment. Transmission impairment. Hidden at the moment, I can. So we will look at this next page. Plus, I want you to answer the questions. I think most of them we have answered today, particularly the calculation one. But the theory answers, yeah, theoretical answers. Okay, you need to do this. Okay, these ones we have already done in the class. Right? Except from 20 onwards. So we will do this in our lecture 3. There are a few other supplementary materials. Please do look at that in your spare time.